Hello, listeners. This is Mike, your host. If you are enjoying these archive episodes, please consider supporting the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange donate button or the Patreon link. Hopefully, with your support, I can continue to release these archive episodes. Thanks. Hello and welcome. This is Michael Annis, and you're listening to episode 143 of the Space Rocket History Podcast. And now, the first Soyuz automatic docking and the secret plan. After 1957, the Soviets became accustomed to achieving world's first in space accomplishments. Nevertheless, 10 years later, they were not confident that they could pull off the world's first automatic rendezvous and docking of two unpiloted Soyuz spacecraft. At the time, the chance for success was estimated only at 50-50. It was a gamble. The U.S., who had begun rendezvous experiments with their Gemini spacecraft in connection with the lunar program, were breathing down the Soviets' necks. But astronaut participation was an essential requirement of the American rendezvous and docking process. The goal of the Soviets was total automatic docking with no cosmonaut on board. During the Soviets' pre-computer phase of space exploration, it was very difficult to perform rendezvous and docking in a purely automatic mode. But they were determined to try. To understand the difficulty of the problem, consider this. Two spacecrafts with a mass of 6 metric tons, each flying around Earth, each on its own orbit, at speeds in excess of 8 kilometers per second. The spacecrafts needed to see one another in order to establish reliable reciprocal radio or optical contact, to begin rendezvous using the power of their onboard propulsion systems, and to approach one another at a relative velocity of centimeters rather than kilometers per second. At the same time, their mutual alignment had to be precise enough to ensure reliable mechanical engagement, subsequent latching, and the mating of multi-contact electrical and hydraulic connectors. But why did the Soviets need to be able to dock without a cosmonaut? Well, the U.S. had proclaimed their goal of landing a man on the moon before 1970. The planned N-1 launch vehicle would not be ready in time to beat the Americans, so the Soviets had to use equipment that was available. This meant using the old reliable Semyorka as a launch vehicle. The first goal was to achieve a circumlunar flight with no landing. This required the development of 3 types of new Soyuz spacecraft, 7K, 9K, and 11K. At the same time, 4 successive launches needed to be conducted using a Semyorka-based launch vehicle to accomplish a circumlunar flight. The 9K rocket would be the first to be inserted in orbit in an unfueled state. The 9K was intended to boost the piloted spacecraft toward the moon. Now, with the 9K in orbit, the 11K refueling spacecrafts would be inserted into orbit in succession. One by one, they would automatically dock with the 9K and fill it with fuel and oxidizer. And when the job was done, they would automatically undock. When the ground was confident that everything was fine on board the 9K in orbit, the two-seater piloted 7K spacecraft would be inserted into orbit. After docking with the 9K, using the engines and propellant of the 9K, this stack would be accelerated toward the Moon. After boost to circumlunar flight, the 9K would be discarded from the stack. Following the flight around the Moon, the piloted 7K would return to Earth. In all, the design called for a minimum of 3 automatic rendezvous and dockings. As the design evolved, the plan changed to use 2 launch vehicles and 2 spacecrafts for a single in-orbit assembly. The spacecraft was designated 7K OK. The 9K and the 11K would not be needed. Instead, docking would be achieved by using 2 models of the 7K OK, the active and passive models. The first phase of docking was called the far approach. Ballistics specialists determined the date and precise time of the launches for this segment, processed the ground telemetry station's orbital parameter measurements as rapidly as possible, and drew up projections for each orbit. They determined the radio communication zones and developed the orbital correction program for each of the 2 approaching spacecraft. In the far approach segment, the rendezvous of the spacecraft was controlled by instructions from the Command and Measurement Complex ground stations. The ballistic specialists calculated the magnitude, place, time, and direction of the correction burns. Before a stipulated correction burn, it was necessary to do several things. First, orient the spacecraft for a boost or break, sometimes at an angle to the orbital plane. Second, load the set point determining the operating time of the correction engine unit or the value of the apparent velocity into the control system memory. Third, issue a complex sequence of commands at the right time to prepare and fire the correction engine. Fourth, ensure the reliable stabilization of the spacecraft during correction engine operation. And fifth, shut down the engine when the stipulated apparent velocity was reached and immediately transfer the spacecraft into orbital orientation or into solar inertia spin mode to charge the onboard batteries from the solar array. During the spacecraft's next orbit in the coverage zone, the ground telemetry stations took measurements and transmitted the results and expressed telemetry data to the ballistics centers. Everything had to be rapidly processed and reported to the Flight Control Operations Group. The human factor played a decisive role in the reliability of the far approach phase. It wasn't just the ballistics specialist who could commit an error using the complex ground-based computers. The myriad of auxiliary services, including the machine operators at the diesel-electric power plants at the ground stations, could break up a correction session. Even during training sessions on the command radio link control panels, ground radio operators sometimes entered an erroneous setting, or, due to a magnetic storm or unexpected interference, communicators were in a position to delay the transmission of information to the center, and so on. One could come up with dozens of possible failures because hundreds of people supported this phase. Once the vehicles were less than 25 kilometers from one another, the close approach phase began. The first sign of this was the presence of the lock-on flag. This meant that the active vehicle radio system had detected the passive vehicle in space having received its radio response. A completely automatic rendezvous and final approach began. The automatic rendezvous segment in the flight program passed through all the coverage zones of the Command and Measurement Complex tracking stations. intervention from the ground was impossible. The human factor was eliminated. Reliability was determined first and foremost by the Eagle radio system, developed at Tracking Station 648, and by the Relay Analog Motion Control System, developed by OKB-1. With the procedure now understood, we can proceed to the mission. At Yevpatoria Tracking Station number 16 Control Center, in October 1967, just one day after the successful Venera 4 probe encountered Venus, planning began for the flight control of the two unpiloted 7K OK vehicles, number 5 and number 6. Both of these vehicles would be called Cosmos, but for training purposes, in hopes of making the next two vehicles piloted, they were assigned code names of Baikal and Amur. Now, after the death of Komarov, extensive modifications had been made on all the systems. Now, more test procedures were performed at the control and measurement station, especially at the engineering facility, and they were more stringent. Many errors occurred with the modified parachute system during the airplane drops in Feodosia. The military representatives and the developers themselves were particularly attentive to any glitch involving the descent and landing systems. On October 16th, the State Commission made the decision for the first launch during the period from October 25th to the 27th. Then something odd happened. At the meeting, Mission suddenly announced that the primary objectives of the joint flight of the two unpiloted 7K OK spacecraft would be to test the reliability of all the systems, including the modified parachute system, and to execute maneuvers for rendezvous, but there would be no automatic docking mission. To the great satisfaction of Marshal Rudenko, General Kamanin, and the cosmonauts, Mission said that we would practice final approach and docking during subsequent piloted launches. But that was very upsetting news to Armen Matsakanyan, the main architect behind the Eagle, and to Boris Chertok. Which brings us to the secret plan. Chertok and Matsakanyan agreed upon a plan. If there were no serious problems on the active vehicle after checking out its systems on orbit, and if the second passive vehicle was inserted into orbit, then being part of the main operations control group as technical chief, Chertok would be able to persuade everyone necessary to take the risk to attempt docking. For the plan to work, they needed to prepare a program at the two ground telemetry stations to supply power to the Eagle radio system and switch the control system to rendezvous mode. Upon issuing the command from Yevpatoria without seeking permission, Chertok would start up these programs on both vehicles, and after that, it would be up to the Eagle system. If docking were to fall through, they would be able to claim that no such mission had been assigned, and if a miracle were to happen, then the victors would not be judged. Flight Director Aganzanov and Tregrub supported the secret plan, and accordingly they tasked the ballistic control and analysis groups with activating the rendezvous mode. The active Amur was supposed to fly solo for almost 3 days. After this, the status of its systems would be reported to the State Commission in Tyrotam. If, in accordance with the ballistics experts' forecast, Amur's orbit correction guaranteed that it would fly over the firing range launch site during its 49th orbit, then the Baikal spacecraft would be launched. The end of the third day and the beginning of the fourth day would be the most stressful. During the minutes after Baikal's entry into orbit, the ballistics experts would have to determine its parameters, and the main operations control group would have to make the decision whether to go for rendezvous or execute an additional maneuver. Throughout the entire flight, it would be necessary to keep a particularly close watch on the consumption of propulsion fluid and the recharging of the batteries from the solar arrays. Now on to the flight. On the morning of October 27th, the order was given to report to the State Commission the complete readiness of the main operations control group and the entire command and measurement complex. At 0800 hours, T-minus 4 hours was announced. At 12:30 hours, the 7K-OK vehicle number 6, Amur, was launched from site number 31. TASS was notified of its name, Cosmos 186. On the second orbit, the solar arrays and all the system's antennas were deployed. The spacecraft had stabilized normally, and it was in solar inertial spin mode. Everything was working. Solar current was normal, the buffer batteries were charging, and even the usually fretful thermal engineers announced that there had been no glitches. During the fourth orbit, settings were entered to test the main approach and correction engine and stabilization using the docking and attitude control engines. Everything worked. The first day ended with optimistic predictions. However, trouble started on the second day. Orbital corrections during the 17th orbit failed. Once again, the 45K Sunstar sensor did not work. Then there were malfunctions while loading settings into the long-range radio communication system. Another attempt at orbital correction during the 31st orbit failed due to a delay in issuing baseline data to the tracking station. The ionic orientation failed due to the spacecraft's movement through ion pockets. But through hard work and almost 3 sleepless days, Amur was brought into a mode that was suitable for a rendezvous with Baikal. The third day ended in suspense, awaiting the launch of Baikal. Baikal lifted off successfully from site number 1 at 11:12 hours 46 seconds on October 30th. TASS was informed that Cosmos 188 had been launched. During the 49th orbit, the Ballistics Center reported that the distance between the two spacecraft was just 24 kilometers, and for the time being, they predicted no clear tendency toward rapid separation. As planned, when the pair of spacecraft departed from Vision in pursuit via circular orbit, Aganzanov gave the command for rendezvous. Chertok then reported the secret plan for docking to Mission and Kirimov. But instead of the anticipated tongue lashing, he was applauded for his efforts. Both vehicles departed from the coverage zone for commands and observations, and somewhere over the ocean, without assistance and monitoring, they would attempt to rendezvous. At this point, everyone could only wait and speculate. Then, finally, stammering with excitement, the shortwave systems developer whispered to Chertok that there was a sign of docking, but communications was so unsteady that it was better to wait until the beginning of the communication session. The developers of Igla and the docking assembly were sweating it out more than anyone. For them, this was their first real exam. For 1 hour, as the two spacecrafts maneuvered over the Pacific and Atlantic Oceans and Africa, worries, debates, and predictions gripped everyone. The control group could not intervene in the process at all, and when the flight director, Aganzanov, announced over the public address system the 5-minute warning until the beginning of the communication session, an unusually large number of people crammed into the large main operations control room, everyone was anxious to see if history had been made. The telemetry service and television experts understood that first and foremost, they must give a rapid response to the question, has an historic event taken place or not? No one needed a special pep talk about the need to be extremely vigilant. A television monitor was placed so that the main operations and control group directors could view the screen while still manning their telephones. Yevpatoria Tracking Station 16 was the first tracking station on Soviet territory to encounter the vehicles flying from the west. The antennas of all the facilities were pointing toward the southwest, inclined to the horizon and standing by. Then the report came in. All facilities have reception. Next, the report from the telemetry operators. We have the capture and docking flag. Realizing not only the technical but also the political significance of the information, Agansanov quickly replied over the microphone. Carefully recheck and report once again. And then came the report again. Literally howled. They're docked. Then the gray image jostling about on the television screen showed out the stationary contours of the 7K OK structure. The television camera of the active spacecraft was transmitting an image of the passive spacecraft, which was stationary in relation to it. Someone shouted, "They're docked!" Now there was no doubt. Docking had occurred. The hush exploded into applause. Someone even shouted, "Hurrah!" Everyone turned to one another with bear hugs and handshakes. When the first wave of elation had finally subsided, and the analysis group had managed to get to work thoroughly processing the information obtained during the replay of the onboard memory recordings, they learned that rendezvous had gone slightly awry, and the latching process had not been completed. A gap remained between the two vehicles, and the power connectors had not been mated. That evening, Mission, Kerimov, Feoktistok, Kamanin, and Gagarin flew in from the firing range. At a joint session of the State Commission and the Technical Operational Management Team, the dramatic reports of how the whole thing actually happened were given. The rendezvous process began from a range of 24 kilometers between the two vehicles. Mutual orientation took 127 seconds. The vehicles were separating at a rate of 90 kilometers per hour. Amur needed to stop separation and begin maneuvering using the approach and correction engines without releasing Baikal from radio lock-on. Amur made more than 30 attitude maneuvers and fired the approach and correction engines 28 times. At a range of 350 meters, the rendezvous process actually switched to the final approach mode, during which the approach and attitude control engines fired 17 times. The entire rendezvous process, up to the point of the mechanical capture, lasted 54 minutes. Approach and correction engine and approach and attitude control engine propellant was consumed in excess of every calculation. As soon as the probe of the active docking assembly came into contact with the passive docking port, the Igla shut down. Mechanical capture superseded radio lock-on, and the latching process began. Telemetry clearly pinpointed the latching process was not completed. The connectors providing an electrical interface between the two vehicles failed to mate. Something clearly prevented the drives from completely joining Amur and Baikal. According to the analysis of the docking experts, a gap of 85 millimeters remained between them, but the spacecrafts were rigidly mated. The television image proved that. The dynamic process of rendezvous was clearly abnormal. Because of this, working groups were formed for a detailed analysis of the operation of Eagle and the Rendezvous Control Unit. An investigation would be conducted at the factory or at the engineering facility on what had prevented latching. It was risky to fly for a long period of time in a not fully docked condition. After 2 orbits, the undocked command was issued, and the television image showed the process of the spacecraft's slow separation. Now the concern turned to preparation for the spacecraft's return to the ground in the guided descent mode. However, once again, the 45K optical sensor was displaying erratic operation. Lighting conditions were clearly jamming the star signal, so the spacecraft couldn't be set up to begin a guided descent. On October 31st, during the 65th orbit, Amur made a soft landing in ballistics descent mode, but the Soviets needed to verify the reliability of controlled descent. They tinkered with the Baikal for another 24 hours, trying to understand what was going on with the star sensor. Realizing that they couldn't rely on it for this spacecraft either, they made the decision to perform orientation for descent using the ionic system. They still had enough propellant for all sorts of experiments on Baikal, but Kirimov and mission, inspired by the congratulations from the Central Committee and Council of Ministers, insisted that Baikal be returned to Earth by any means. So, on November 2nd, after setting up the spacecraft using the ionic system, the commands were issued to start up the descent cycle programs. The ionic system failed somewhere in the Brazilian magnetic anomaly, and the braking burn sent the spacecraft toward Earth on a long, flat trajectory that emerged beyond the limits of the authorized corridor in the Soviet Union. The self-destruct system automatically destroyed 7K OK vehicle number 5. This time, the tracking system and the anti-ballistic missile system closely monitored the descent module's trajectory. The vehicle was blown up after it passed over Irkutsk. From these flights, the Soviets determined that the ionic orientation system was unreliable. The system needed to be supplemented with an infrared sensor in order to provide a reliable pitch and roll orientation. The 45K sun-star sensor needed to be thoroughly studied and made to reliably track stars. The Eagle and Rendezvous Control Unit needed work in order to refine rendezvous dynamics, and finally, they needed to find out what was preventing the spacecraft from closing the gap completely. In lieu of the problems encountered with this mission, it was decided that another unmanned docking attempt would be made before a manned flight. It was decided that 7K OK vehicles numbers 7 and 8 would be prepared for unpiloted launch for a flight entailing a mandatory refinement of the rendezvous process and verification of the guided descent system. In conclusion, on November 1st, 1967, Pravda published the following greeting, quote, "We scientists, designers, engineers, technicians, and workers who took part in the development and launch of the 2 satellites, Cosmos 186 and Cosmos 188, report the successful execution of the world's first automatic docking and undocking of 2 spacecrafts on orbit. We dedicate this new achievement of Soviet science and technology to the 50th anniversary of the Soviet rule." End quote. Docking on the first attempt, albeit not fully complete, but in time for the 50th anniversary of the glorious October Revolution, was a victory for the Soviets. Thanks for listening to this archive episode of the Space Rocket History Podcast. If you are financially able, please support the podcast by going to the homepage spacerockethistory.com and clicking on the orange donate button or the Patreon link. Thanks.